In this chapter, we'll define the sampling distribution of a continuous random variable x that is normally distributed. So let's start off the discussion with finding the average height of all adult women in United States. Remember that the height of women is normally distributed. So if x is our variable, that is the height of women in United States, then the distribution of this continuous random variable is bell-shaped. The average height of all adult American women is denoted by the Greek letter mu, because what we're talking about here is the population mean. So it is the mean height of all adult women. So the word all tells us it is that population mean. So the first question says, what is the process that would give us the exact average height or the mean height of all women in United States? So theoretically, this is how you would find it. You would collect data first, that is the height of each woman in United States. Once that is done, we'd add all the numbers and divide by the total number of numbers, and then that would give us the actual mean or the true mean of all adult women in United States. Now this is not a practical solution because the sample size, or rather the population, is huge and it is almost impossible to collect that sort of data. So the next question is, what would you do if you were asked to find the mean height of all adult women in United States? So if we were asked to find the mean height of all adult women in United States, we would first find a sample of women that is reasonably big. So that is a good sized sample, and find the sample mean, which is x bar. So find the mean of the heights of all women in that particular sample, which is x bar. We're talking about the sample mean, so it's denoted by x bar. And then we could kind of say that the true mean of all US women is close to the number x bar. So this would just be an estimate. X bar would be close to the actual mean, but it is not going to be equal to the exact mean height. So that it would be pretty close if the sample size is large enough. How do we make our estimate from the mean large enough? So when does x bar come close enough to the actual mean mu? If we make the sample size n is the sample size, the number of things in our sample is called the sample size. If we make our sample large or very large, then x bar gets closer and closer to mu as the sample gets larger and larger. So increasing the sample size would get the sample mean closer and closer to the true or the actual mean. Using the example on this page, I'm going to define a sampling distribution of a continuous random variable x. Now suppose we find multiple samples, 1000 samples, simple random samples, so unbiased samples, containing 25 people, each containing 25 people. So if we have 1000 independent samples and each contains exactly 25 people. So the first question is, how many subjects are in each simple random sample? Remember we said let's select samples of a fixed size, which is 25. So each sample contains 25 people. How many means do we have? Every sample gives us the sample mean. So in any particular sample, we add all the numbers and divide by the total number of numbers, and that would give us the x bar, which is the sample mean. So if we have 1000 different samples, we can find 1000 different means, one coming from each sample. Will these means be exactly the same? And the answer is no, because each is a separate simple random sample and there is variation among samples, so therefore the means of these samples don't necessarily have to be the same and they are going to be different. Now think about what we're doing. We collected multiple samples, many samples, each containing 25. For each, we're going to figure out what the x bar is. So each sample is going to give us an x bar. Now notice that none of these x bars, so that's x1 bar, x2 bar, x3 bar, and so on, and the last one is x subscript 1000 bar. And note that there are 1000 such samples, and each sample gives us an x bar. So we have 1000 different x bars coming from a fixed sample size of 25. Now, what we do with all these numbers, we have 1000 numbers, and each is a mean. So our new variable is x bar because no two means will be the same most likely. So the mean that we get from a simple random sample of 25 each is a variable, and that's important to understand. Now once we've collected all the data, we have 1000 means from 1000 different samples. So our new variable is x bar. So we have the mean, the sample means coming from 1000 different samples. Once we collect all those numbers and then we make a histogram from those numbers, once we make a histogram, we're going to get a bell-shaped distribution. Now notice that on the x-axis, the variable is no longer x, it is x bar. Now what is the variable in this particular process? Notice that the variable here in this new process that I'm describing is x bar, the sample mean, because the sample mean is going to differ from one sample to another. So it is a variable, and that's the variable that we have made a histogram for, and we notice that the histogram for the variable, which is x bar, is also normally distributed. So what's the variable in the process? It's x bar. What kind of a distribution is this? This is clearly a normal distribution. What do you think is the center of this distribution? The center of the distribution is always mu, the population mean. So we've collected all the x bars, made a histogram out of it. The histogram shows us the shape of the distribution. The shape is roughly bell-shaped symmetrical distribution, which is a normal bell-shaped normal distribution or a bell-shaped distribution. So what kind of a distribution is this? Clearly it is normal because it's bell-shaped. The next question is, what do you think is the center of this distribution? The center of the distribution is the mean mu, and that is the actual or the population mean mu. Now here I'm going to once again explain what a sampling distribution of the means is. So we collect many simple random samples of a fixed size n. N could be 30, it could be 25, it could be 50, it could be higher. So we first, the important thing to understand is that you have many samples, many samples. So more than 1,000 samples, for example. So once we have many samples, for each sample we calculate x bar, which is the sample mean. Again, note that the sample means are not all going to be the same. It's possible that they are different. In fact, it's very likely that they're all different. So we label the subscript so we know these are particular sample means coming from specific samples, many samples. So we have a bunch of numbers here, and all these numbers are the x bars that come from the various samples that we've collected. So the variable here in this process is x bar. X bar is the variable since we're calculating the x bar, which is the population mean, and they're all going to be different, so that's what makes it a variable. So we start off with a regular normal distribution. This is a regular normal distribution where the center is the mean and the standard deviation is sigma. So the center is mu and the standard deviation is sigma. So the regular normal distribution is bell-shaped and it has mean as the center and sigma as the standard deviation. So what do we do next? We collect multiple samples of these measurements x, multiple samples of a fixed size, let's say n equals 25, from the population, and we find the mean of each of these samples, and that gives us many means. So the mean now becomes our new variable. So that's our new variable. And once we make a histogram, it shows the shape of the distribution, and you'll notice that the shape of the distribution is a normal bell-shaped distribution. Once again, here is the diagram that I have of this process. We have a population. This is our population. We collect multiple samples from the population, simple random samples, unbiased samples from the population, each of a fixed size, and here we're going to make this a general sample size, so that would be n, so that's sample size n. So we collect multiple simple random samples, but each sample is of size n, which is a fixed number. Once we have all these simple random samples, we find the average of each simple random sample and we call it x bar. But note that these x bars are going to be different. They're not necessarily the same because each x bar comes from a different simple random sample. So since they're going to be different and they're numbers, fixed numbers that are going to be different, we're going to attach subscripts to tell us that x1 bar comes from the first sample, x2 bar comes from the second sample, x3 bar comes from the third sample, and so on. Notice here that the new variable that we have here is x bar. It's no longer x, since we are now looking at the various x bars that are not necessarily the same because they're coming from different simple random samples. Our new variable is x bar. So we have multiple means, and that is our new variable x bar. We collect all these means. There are many of these, and they're not all necessarily the same, and that's why the means are the mean now becomes the variable, the new variable. We collect all those means and make a histogram based on all that data that we get from the means, the various means. So our variable is no longer x, it's x bar. So we have a histogram, and the important thing here is when we make the histogram of all the means, it's again a bell-shaped curve. So the distribution of the original variable x is normally distributed. After following the process and finding several simple random samples and finding the means from each of those samples, our new variable becomes x bar, and when we make a histogram of all the x bars, it turns out that the distribution is again bell-shaped. This new distribution, that is the bell-shaped distribution, has center mean and standard deviation sigma over radical n. So the center of this distribution, the sampling distribution, is mu, but the standard deviation is not just sigma, it is sigma over radical n. It depends on the sample size of the fixed sample size in the process. So sigma over radical n is the standard deviation of the sampling distribution. So we start off with a normal distribution with center mu and standard deviation sigma, and using that we find a new normal distribution with center mean and standard deviation sigma over radical n. If the variable here is x, the variable here is x bar. So the distribution of x bar has mean mu and standard deviation sigma over n, and this is called the sampling distribution.